Okay, super. Let me zoom in. All right. Number one. The map below shows four major time zones of the United States. The locations of Boston and San Diego are shown. What is the time in Boston when it is 11 a.m. in San Diego? So they made it really easy. Basically, they just diced it up by the time zones. They don't normally do this for you. So this one you just count, right? So if it is 11 o'clock in San Diego, which is part of Pacific time, if you go to Mountain time, that would be 12 noon, 1 p.m., 2 p.m. So that was pretty easy. But many times they'll actually dice it up with longitudinal lines. And you have to remember that each longitudinal line that's 15 degrees apart, that's going to be 1 hour. So normally they'll have it as Boston is 75. And then, well, what's 75 plus 15? That would be 90. They would have the next one as 90, and that would be the central time zone. Then you would add another 15 to that. That would get you to 105. That would be mountain time zone. That kind of makes sense. But just remember, it's 15 degrees per hour, or if you're lucky enough to get this one, it is just by time zone. Okay, next one, number two. This should be pretty familiar. The diagram below represents the spectral lines from the light emitted from a mixture of two gaseous elements in a laboratory on Earth. So you can see that we have wavelengths running from blue to red. So there's your spectrum. And it says, if the same two elements were detected in a distant star that was moving away from Earth, how would the spectral lines appear? So once again, if the same two elements were detected in a distant star that was moving away from the Earth, how would they appear? If something's moving away from you, everything is going to appear to shift to the red. So everything would appear to shift to the red end. Now, the opposite would be true if they mentioned a star that was moving towards you. If a star is moving towards you, its wavelength would increase. Now, if you don't remember that, there's actually a pretty easy way to think about it. So here's your electromagnetic spectrum. And you can see that the wavelength decreases, meaning that the frequency is increasing. The distance between one peak and the next is shorter because everything's getting all crunched up. If something's coming towards you, it's kind of like running into its own waves that are going out to you, making it appear to be a shorter wavelength. And that's why if something's moving towards you, you're going to move to the blue violet. And if something is moving away from you, you'll be increasing the wavelength, moving to the red. And again, basically everything in this universe is moving away from us. Number three. The diagram below shows the Earth in orbit around the Sun and the Moon in orbit around the Earth. M1 and M2 indicate positions of the Moon in its orbit where the eclipses might be seen from Earth. Which table correctly matches each type of eclipse with the orbital position of the Moon and the cause of each eclipse? Okay, so here's the Sun, here's the Earth. We've got the Moon in position 1. In between the Sun and the Earth. If the Moon is in between the Sun and the Earth, that means there's a possibility that it can block the Sun, right? So we would call that a solar eclipse. So a solar eclipse needs to say M1, solar eclipse M1, so that's a possible answer. And Earth's shadow falls on the Moon? No, we call that a lunar eclipse. The Moon's shadow falls on Earth? Yes. So our answer looks like it would be 2. Let's just double check that where it says lunar M2, Earth's shadow on the Moon. Yeah, there's M2. There's Earth. Our shadow would be coming out behind the Earth and blocking the Moon from that perspective. All right, number 4. The timeline below represents the entire geologic history of Earth. The lettered dots on the timeline represent events in the Earth's history. Which lettered dot best indicates the geologic time when humans first appeared on Earth? When did humans show up? ESRT page 8 and 9. If you take a look at page 8, you can see that humans appeared during the Pleistocene. The Pleistocene epoch happened between 1.8 million years ago and 0.01 million years ago. So basically about a million years ago. All right, so where would a million years fall on this chart? Well, origin of the Earth would be 4,600 million years ago. That's a long time ago. So that would mean that humans would have to be A. There's really no other way around that. In fact, I would move A a little closer to that present day dot. Hi, Simone. 5. Compared to our solar system, the universe is younger, smaller, and contains fewer stars. Well, the universe is much, much larger. So it couldn't possibly be 1. It is younger, larger, contains more stars. Well, it does contain more stars, but we're part of the universe. So how could the universe be younger than the solar system? That doesn't make sense. So it would obviously have to be older, larger, and contain more stars. The answer is 4. 6. Which motion allows an observer on Earth to view different constellations throughout the year? Why don't you take a moment and drop it in the chat? What do you think the answer is? Which motion would allow an observer on Earth to view different constellations throughout the year? Here's the link for those of you guys that just joined late. Garentia says 1. Any other possibilities? I mean, this would make sense. It could be the constellations orbiting the Earth, but not in this universe. So the constellations are very, very far away. So it would take way too long for it to go around. When we're talking about, throughout the year, why we could see different ones, it would be the Earth orbiting the sun. So yeah, it is number 1. Very good, Simone. Very good, Karencha. 7. What is the approximate location of the Tasman hotspot in the Pacific Ocean? All right, back to the reference tables. So hotspots are what? They're a geologic event, right? So we're probably going to want to go to one of the charts that shows geology. This shows ocean currents, so that's not going to work. Here we go. And there's the Tasman hotspot. Yeah, it's just off the coast of Australia. And it appears to be like pretty much right on the 160. Now notice we have a 160 here and we have a 160 here. Well, you have to remember the direction goes based off the prime meridian. If this spot right here is 0 degrees, that's the prime meridian, that means that this one would be 20 west, 40 west, 60 west, 180, so we're at the exact opposite of the prime meridian, also known as the international dateline, and now we're at 160. So this would be 160 east. Now let's go up. It seems to be, let's take a look on the other side. It seems to be pretty close to the 40, maybe a little less than 40. And we're definitely in the southern hemisphere because we're lower than the equator. So I would say we're at like maybe 37 south and maybe 160 east. So let's jump back. Here we go. 36 south, 160 east. Not too bad. All right, number 8. I want you guys to try this one independently. Most ozone is found in a region of Earth's atmosphere between 10 and 20 miles above the Earth's surface. This temperature zone of the atmosphere is known as what? You're going to need your reference table. And you're going to be on page, what page is this? Page 14. Take a minute. Most ozone is found in a region of the Earth's atmosphere between 10 and 20 miles above the Earth's surface. This temperature zone is known as the what? Jade's thinking stratosphere. Maya also says stratosphere. All right, so let's take a look. Remember, we have kilometers on one side and miles on the other. The document says between 10 and 20 miles. If that's 0 and that's 25, that would be 5, 10, 15, 20, 25. All right, so we're going by fives. So between 10 and 20 would be here and here. So yeah, we would be part of the stratosphere. In fact, if you take a look at the temperature curve here, you could see at the surface, our median or our average temperature is about 15 degrees Celsius. So that's a bit cooler than room temperature. It's around room temperature, a little bit lower. As we move up through the atmosphere, the troposphere, you'll notice the temperature drops. When we hit the tropopause, the temperature stops decreasing, becomes relatively constant at negative 55 degrees Celsius, and then eventually it starts to warm up again. Why is that? Well, there's no coincidence that it's because of the ozone layer. The ozone layer actually takes ultraviolet light from the sun and it absorbs it and it turns it into heat. And this actually protects us from getting sunburn, skin cancer, and cataracts in our eyes. So very, very important, the ozone layer is. Okay, back here. So yeah, the correct answer was 3. Number 9, the Coriolis effect, which causes the curving of planetary winds as a direct result of what? So we didn't talk about this in class yet, but the Coriolis effect is an interaction between the fact that the Earth is a spinning ball in space. It's a spinning oblate spheroid. As it spins, wind is trying to go from one spot to another, and that causes the wind to spin. You ever wonder why a hurricane turns? It's because of the Coriolis effect. So the answer would be 4, the spinning of Earth on its axis. Okay, I'm going to skip number 10 just because we didn't learn it in class yet. 11, ESRT page 1. It says when 1 gram of liquid water at its boiling point is changed into water vapor. Well, what do we call liquid water when it boils? Yeah, you could call it boiling, but there's another term for that. Sometimes we call it vaporization. So let's go back to our reference table. We're going to go to page 1. And if you take a look here under properties of water, you could see heat energy gained during vaporization. It's another word for boiling, essentially, or evaporation. Same deal. 2,260 joules per gram. Now, a joule is a measurement of energy, and a gram is a measurement of mass. So for each gram that the water weighs, you need a certain amount of energy put into it to evaporate it. But we already knew this, right? I mean, like if you take water and you splash it onto a hot frying pan, it's going to boil and vaporize instantly. If you throw it on your desk at room temperature, it'll take a while. And it's all about how much energy can be absorbed. So let's head back. So is it 2,260 joules gained or released? Well, if we're boiling the water, it's energy gained because the water has to gain energy somehow. And if we're boiling it, on a stove, well, it's gaining it through the fire that's beneath it. Very good. 12. Cross-section below represents some processes of the water cycle. Arrows represent the infiltration of water. The dashed line labeled X represents the uppermost level of earth material that is saturated by groundwater. What is indicated by the dashed line labeled X? So you can see here we have rain or some kind of precipitation. We have infiltration. That's when water goes into the ground. We have the zone of saturation, which is the groundwater. And we have the very top of the zone of saturation, or the very top of the groundwater. And we call that the water table. Yeah. So a watershed is the entire area that is causing the water to dump out into the ocean. So this line right here, if they were referencing that, then yeah, we would call that the watershed. But because right here we're talking about that line, it would be the water table. 13. Which index fossil in sedimentary surface bedrock most likely indicates that a marine environment once existed in the region where sediments were deposited? Okay, so there's a couple interesting things here. What is an index fossil? Does anybody remember? No takers? Don't be shy. Well, it's definitely a fossil. What does an index in a book do for you? Well, the index at the end helps me figure out where certain things are. An index fossil helps me figure out where certain things are. Index fossils are organisms that were in a wide area, but only for a short period of time. Can we think of anything that's been in a wide area for a short period of time? Humans, dogs, cats, they've been all over the whole planet only for a short period of time. But to be honest with you, they're not very good index fossils because they're all very recent. We want to know what happened a long time ago. So the classic ones would be trilobites. Because trilobites existed for quite a long period of time, but there were different types that we can go to. So if we jump back to page, what is it? I think it was page 8. Page 8 and 9. Yeah, if we go on to page 9, you can see all these letters here. Do you remember what that was for? These are all index fossils, or maybe just important fossils. Some of them aren't index, but they're fossils that were over, for the most part, a wide area, relatively easy to find. And if you do find them, you know what time period they were from. Let me see if I can zoom out. I can't put two on one page, huh? Okay. Well, let's hop back to this one. Sedimentary bedrock indicates a marine environment. What does marine mean? Trilobites, I'll show you in a second. So a marine environment is an ocean environment, salt water. Once existed in a region where sediments were deposited. Okay, so let's take a look at each of these. Mastodons. Well, let's take a look at a picture of a mastodon. Who's a mastodon? There's a mastodon. Does that look like an aquatic creature to you, or a marine creature, like it lives in the ocean? I'd have to say no. No to mastodons. Next, we have condors. Well, we already know that's not true. We know what a condor is, right? Condor is a bird. Where is he? Do they? Oh, I guess they don't show you a picture of it. Oh, no, there he is. There's your condor. Definitely not a marine creature. Let's take a look at another one. Eospifer. Eospifer. There's Eospifer. He looks like a seashell. I'm going to say that, yeah, that's probably... No problem, Jade. I'm going to say that's probably a seashell. And lastly, we've got Coleophysis. Let's see if Coleophysis could be a marine creature. I'm not seeing it on this page. There's Coleophysis. Oh, Coleophysis is a dinosaur. I would say that he's probably not a marine organism. So I guess that gives us our answer. The answer would be Eospifer. Eospifer. Spirifer. Not a very common one. Now, just to answer your question about trilobites, these guys are trilobites. This guy, A, B, C. Please don't ask me to pronounce them. But you can see here, the trilobites are all in this section. They live for quite a long time, but we've got some nice ones there that are only in certain time periods that, you know, if we find letter C, we know it happened during, actually, let's do this. If we find letter A, we know it happened during the Cambrian time period. Because if you go straight across from Cambrian, you would pop up to A. It's kind of annoying that the papers, I can't get them side to side, but whatever. Okay, 14. All right, we're going to skip this because we didn't learn this yet. Excuse me. 15. Cross-section below indicates the geologic ages of the bedrock beneath the state of Michigan. These rocks formed from sediments deposited in an ancient depositional basin. This region is called the Michigan Basin. Glacial deposits cover most of the surface. Which process most likely caused the formation of the Michigan Basin? Okay, so I see glacial deposits. We see Cambrian, Ordovician, Silurian, Devonian, Mississippian. It's like sedimentary rock was dropped down here. So could that be caused by uplift? Faulting, metamorphism, and downwarp. Well, downwarping is not a thing. Cross-section below indicates geologic ages. These rocks form from sediments. This region is called the Michigan Basin. Glacial deposits cover. Well, I'll tell you what it's not. It's not downwarping because it's not a thing. It's not metamorphism because we don't see any of that. We don't see anything that's being pressurized. We don't see any lava being spilled on it. It's definitely not faulting, so we don't see any cracks in it. So that really just leaves us with uplift. I'm a little bit like stretching my mind as to how it would be uplift here. The only thing I could imagine is you can see here where it says Precambrian. This part kind of rolls up. This part over here kind of rolls up too. So these two areas have uplift because like we're looking at some folding, possibly. I don't know, weird. It's got to be uplift though. All right, 16. Cross-section below represents prevailing winds shown by arrows moving over a coastal mountain range. Letters A through D represent locations on the Earth's surface. Which location would most likely have cloud cover and precipitation? So what you're looking at here is a mountain range. You see the oceans on one side, and you see your prevailing winds. Prevailing winds, that's the direction the winds generally come from. Now, as those winds hit the mountain, they get pushed up. Now, if you remember what we learned today in class, the higher up you go in the Earth's atmosphere, within the troposphere, the colder it's going to get. So it's going to get real cold at the top of this mountain. Now, the air just came off the water. So this air is wet. What happens if you take wet, humid air and get it really, really cold? You're going to get precipitation. You're going to get rain. So where are we going to have the most cloud cover and rain? Points A and B. Where are you going to get the most rain? Probably point B. Yeah, because as it goes up, that's where it gets cold, and that's where we get the precipitation. Usually on the other side of the mountain range, we get something we call a rain shadow, where it's extremely dry. So if you look at the United States, if we pull up, I'm going to pull up a Google map. And let's put on a satellite view. All right. So if you take a look at American Southwest, or really even like the whole western half of the United States, you'll notice we've got mountains here. Utah's covered mountains, Nevada, Arizona. Take a look at California. California's got some beautiful places in it. But one thing you'll also notice is that, can I rotate? I don't think I can. Well, you see here, there's a mountain range. I'm not sure which range this is, but this mountain range right here, which basically runs the whole length of the continent, any water, wet air, let's say, humid air, that comes over here, goes up the side of this mountain, and it forces it to rain. On the opposite side of it, it's going to be dry. And that's basically why you have this rain shadow, this whole black rock desert. I mean, it even says desert right there. Meanwhile, you've got a forest. So it's like lush, green, and, full of plants. And then on this side, nothing. All because of the mountain ranges. "17. Which Earth's surface would most likely absorb the greatest amount of insolation on a sunny day if all these surfaces have equal areas?" All right. Well, what is insolation? Insolation is a fancy word for incoming solar radiation. So it's sunlight. That's it. So which area would absorb the most sunlight and basically get the hottest? A black parking lot, a white sand beach, the surface of a calm lake, or a snow-covered mountain? Who's going to get the hottest? Yeah, it's a black parking lot. So objects that are dark absorb more insulation than objects that are light colored, and objects that are rough absorb more light, more heat, more energy than objects that are flat. Think about a mirror. A mirror is extremely flat and the energy bounces right off of it. And a parking lot is pretty rough. 18. Most of the infrared radiation given off by the Earth's surface is absorbed in the Earth's atmosphere by greenhouse gases such as water vapor, carbon dioxide, and what? So there are 3 key gases, and I'm just going to give this one to you because we didn't learn this yet, and it's kind of a memorization one. Methane. So, and I'm not trying to be gross here, but one of the main causes of methane is animal flatulence, or, cow farts is one of the biggest things. Yep. And humans, we raise cattle because we like to have hot dogs and hamburgers, and we like to have milk. And you can't have that stuff without the cows. And methane is just one of those byproducts. 19. The X on the map below indicates a region of the state of Washington, where the state of Washington is located on a present day North American continent. During which geologic period was the region of Washington state closest to the equator? When was Washington state closest to the equator? So we're going to go back to our reference table, and we're going to look at page, oh, we're right on the page, page 9, our geologic history page. So do you see Washington state on here? If you say you do, you're probably lying. It's kind of tough to tell. So here is North America. Now let's take a look at it again. You can see how they give it to you as this like black blob here, and you have that white X. Now the white X isn't going to be found on the image of the map, but you can guess where it is. And now we want to see it next to the equator. And it looks like right about here, it would probably be closest to the equator. So that was 458 million years ago. Uh-oh, they didn't give us 458 million years. So what now we have to do is jump back to our reference table and find out what time period was during 458 million years ago. So if we slide to that next page over, page 8, what was it, 458? So we would be somewhere in the Ordovician. How do I know? 444, 488, 450 something would be like right in the middle. Answer, 4. 20. A climate event that occurs when surface water in eastern equatorial area of the Pacific Ocean becomes warmer than normal and may cause a warm, dry winter in New York State is, so we didn't learn about this one yet, but this is El Nino. So the El Nino events are a reversal, and we'll talk in more detail about this one. But they're a reversal of the equatorial countercurrent. So right here, you can see this guy, the equatorial countercurrent. I'm still not 100% certain why this happens, and I'm not sure if many scientists are certain why this occurs. It may be part of climate change. But what ends up happening is you can see the black line means warm water. The warm currents of water, they rotate and they flip back the other direction. So instead of getting cold water off the coast of, off the coast of Australia, you get warm water and vice versa. So it ends up causing droughts in Australia, and it ends up killing fish in South America, which is actually pretty bad because a lot of people depend on that as a food source. And then again, it also changes climate patterns up in North America as well. 21. In the New York State rock record, there is no bedrock from the Permian period. Which two other entire geologic periods have no sediment or bedrock in the New York State record? We're going to head back to pages 8 and 9. And you can see here on the top right, we have our New York rock record. You can see some are sediment, some are bedrock, implying igneous. Which ones do we have no record from? Well, we don't have any from the Neogene, because there's nothing here. We don't have anything from the Paleogene, nothing here. We don't have anything from the Permian. Nothing here. And that looks like about it. So let's go back to the question. No rock record, Paleogene, and Neogene. '22. The cross-section below represent two widely separated bedrock outcrops, 1 and 2. Letters A, B, C, and D identify some rock layers. Line XY represents a fault. The rock layers have not been overturned. Which lettered rock layer is the youngest? So who is the youngest out of all these? Well, let's try and match some up. I could see lines with dots, and then I could see lines with dots again. I could see this is shale. That's shale. D and B are probably the same. So I'm going to assume that... Oh, actually, I'm looking at it backwards. This guy is the same as this one. This guy is the same as this one. Yeah, so that is the same. So A here is the same as this one here, so A has to be the youngest. I mean, technically this sandstone here would be even younger, but A would have to be the youngest with a letter on it. All right, 23. Block diagram below represents surface features in a landscape region. Which diagram best represents the general stream drainage pattern of this entire region? Okay, so we had some folding going on, and we have some hills here, and water's obviously going to be going down those, and they're going to be piling up and rolling away as rivers. The answer would have to be 3. I think a common misconception a lot of people put would be number 1. This would be more of an annular pattern. This is what we call terraced. 24. Compared to a landscape that develops in a cool, dry climate, a landscape that develops in a warm, rainy climate most likely will weather and erode slower or faster. Cool, dry climate, a landscape that develops in a warm, rainy climate will erode faster, and the landforms will be more rounded. Okay, we're going to wrap up with this page, so we'll do another 3 and we'll call it a day. 25. The Earth's crustal bedrock at the mid-Atlantic ridge is composed mostly of what? So the bedrock at the mid-Atlantic ridge is going to be made of basalt. Now, if you didn't remember that, you could always go to ESRT page 10 and take a look here. You can see the oceanic crust is made of basalt, where the continental crust would be made of granite. All right, now what is the density of the basaltic crust? Head back. The basaltic crust has a density of 3.0. So our answer would be 4. Okay, 26. A seismic recording station located 4,000 kilometers from the epicenter of an earthquake received the first P wave at 7:10 p.m. Other information that could be determined from this recording was that the earthquake occurred approximately when? Well, I know which time I felt the shaking at the seismic station. I know it was 4,000 kilometers away. Question is, how long does it take for a P wave to travel 4,000 kilometers? ESRT page 11. We're going to find 4,000 kilometers, which is right here. We're going to go up till we hit the P, and then we're going to move across. So the P wave travel time of a 4,000 kilometer away earthquake is approximately 7 minutes. So let's head back. So if it took 7 minutes to get there and I felt it at 7:10, that means it left at about 7:03. Okay, so let's see. 7:03, 7:03. So that's either 1 or 2. And the did the S wave arrive at 7:12, or did it arrive at the station at 7:15? Okay, so let's head back to the reference table. And let's see, for 4,000 kilometers, how long would it have taken the S wave? It would have taken 12 minutes and 40 seconds. I know it's 12:40 because if that's 12, that would be 12:20, that would be 12:40. The answer would be, well, what's 12:03? I'm sorry, what's 7:03 plus 12 minutes and 40 seconds? The answer would be 2. Yeah, this was a tricky one. They want you to pick that, but the answer was 2. And I hope you see why, because it takes an additional 12 minutes and 40 seconds for it to get there, but we didn't depart. The earthquake didn't leave the epicenter until 7:03. 7:03 plus 12:40 gives us 7:15:40. All right, and then the last question, we're calling it a day. Which graph best represents the percentage by mass of elements of the Earth's crust? ESRT, page 1. Percentage by mass. Reference table, page 1. Go to the bottom. Earth's crust, percentage by mass. That's right here. Oxygen is 46. Silicon is 28. 46, 28, 8. 46, 28. Oh, and then all the rest will be built up in that section. So, oh wait, was it oxygen or silicon? I already forgot. Oxygen is the most abundant. So oxygen, silicon, so the answer would be 1. All right, guys. Are we still together in one piece, or are our brains completely melted by this point? Melted halfway. All right, very good. Very good. I'm just going to take a screenshot of everyone's name so everyone gets credit for today. If you have any questions, I'd be more than happy to work with you for the next 12 minutes. Otherwise, I will see you all tomorrow.